Hey everyone. So today we're going to do an interesting problem where we are going to take in a stack and then we are going to reverse the elements in that stack without using any additional data structures. So let's go ahead and jump right into the problem. And the first thing that we need to do, as always, is ask any questions we might have of our interviewer. So, a couple obvious questions come to mind. One is, what type of elements are in this stack? In this case, it doesn't really affect the problem, so I'm just going to assume that it's a stack of integers, and that'll be good enough. And another question we might ask is, we just would maybe clarify the constraints of this problem. So it says no additional data structures, but are we allowed to use extra variables if we store variables in a recursive stack? Is that okay? How exactly what are the bounds of what we can do? So in this case, what we can't do is something like create another stack or another queue or any other data structure like that. But if we want to store variables in a recursive stack and do something recursively, that's totally okay. So things to just clarify with your interviewer, and if there's anything that you don't understand about the problem, definitely a good thing to clarify up front before you start doing the wrong thing. And the last thing that's a really useful question for us to ask in this case is, are we using some generic stack implementation, or are we implementing it ourselves, or do we have access to the underlying data structure? Because let's imagine this problem if we were to implement a stack. So if I was going to implement a stack, I'd probably use a linked list, because that's pretty much the easiest way I can think of to do it. And it would be really easy for me to go and modify that underlying linked list and just reverse the linked list. And if I reverse the linked list, then voila, I've reversed my stack. And that would make this question really easy. But we don't want to assume that in this question and then go off in a totally different direction, because when I pose this question to you now, I'm actually thinking of something totally different, and I want you to use a generic implementation. So I'm going to do this using the standard Java implementation of a stack, as opposed to using a personal or a customized implementation that I can actually modify. So it's good asking these questions is going to inform how we're actually going to approach this problem, because now we know that we're going to have to do something that's going to involve pushing and popping elements to the stack, because that's the only thing that we know that we're able to do with a regular Java implementation of a stack. We know that maybe we might want to use a recursive algorithm, because we know that we are allowed to do that, and that's going to be one of the few ways that we can actually store any values that we pop off the stack. So let's think about how we could actually solve this problem. And I just mentioned this, but the first thing that we can think about is maybe we should be doing this recursively. And the reason why I come to this conclusion is that we know that we're going to have to pop some items off the stack, right? We're going to have to reorder them somehow. You can't add an item below another item without popping off all the items above. And we can't create any data structures to store these popped elements in. So the only way that we could do this without creating an infinite number of variables and assigning all the popped items to these variables, or creating an array, which is not really allowed, is to do this recursively. Because when we do it recursively, as we pop off items, they're stored in the recursive stack. So we know we can do things. For example, we can traverse the stack in order, right? We could do a recursive call down and do something with each element that we pop off, go through to the bottom, and then when we return back up, just push the elements back onto the stack. We could do that, and we could modify all the elements in the stack. Or we could go through the stack in reverse order, right? We could recurse all the way down through and popping elements off, and then we could modify the element and then push it back on, and so on up the stack. So you could do different things like that. You can traverse it in order. You could also do things like, we could recursively add an element to the bottom of the stack, right? Because we could pop off all the elements and pass in the stack and whatever element we wanted to add to the bottom. And when we get to the bottom, you add that element into the bottom, and then you push elements back on up to the top of the stack. So maybe let's think about how we could potentially combine these techniques into what we're trying to do. So let's go ahead and look at, let's say we have a stack here and an empty stack like this. Or actually, sorry, we're just going to have one stack. And let's say we want to So what we want to do is we want to reverse this stack, right? So we can pop off an element from the top, and this will go into our recursive stack. And then we could pop off another element and so on and so forth until we get to the bottom. We could do that, and then we could maybe come up with some way to do this. Or as I mentioned, we can push elements to the bottom of the stack. So let's imagine if we just traversed this stack and we pushed each element to the bottom of the stack. So by doing it recursively. So let's say I start at the top and I just move this 1 to the bottom of the stack. And now all of a sudden I've sort of made progress, right, in reversing this. But now when I get to the 2, I would want to push the 2 to here, to this second space, and that's not going to be so easy to do. So maybe instead we could traverse the stack in reverse order and push item, and then push them to the bottom. So let's say we start at the bottom, and well, we've popped all the elements off the stack now, and we start with the bottom element, and we push that onto the stack, or we push that to the bottom of the stack, which in this case is right here. And then for our next element, we could push that to the bottom of the stack too, which would end up under this 4. And then we could take this 2 and push that to the bottom of the stack, which would end up here. And finally, we take the 1 and push that to the bottom of the stack. And then as you can see here, we've managed to reverse this stack by what we did was traverse the stack in reverse order. So traverse it from the bottom up. And each turn we add our new element to the bottom of the existing stack, thereby reversing it. And there may be a more efficient way to do this, or there's certainly a more efficient way to do this time-wise if we were able to use more space. So if we were able to use, for example, another stack, this would be really easy to do because we could just pop the elements off of one stack onto the other stack and then just return the other stack, and that would be all there was to it. It would be a super simple problem, and it would take linear time because it would only go through the whole stack once. And this is obviously going to take longer, but we are making this trade-off because we can't, by not using the extra space, it's taking us more time. So let's go ahead. We have this potential implementation, and I can't think of a better one off the top of my head anyway, and in the time that is allotted in your interview, you should definitely just, unless you know that there's definitely a better solution, just go with what you have, and you may have time to improve your solution later. So let's go ahead and implement this solution. And there are really 2 parts of this solution, right? There's the insert at bottom of stack, and there's the traversing the stack in reverse order. So I'm going to start with actually implementing the insert at bottom of stack, and that's going to be a private method that's going to be just called insert at bottom, and it's going to take in a stack. In this case, I'm doing a stack of integers, and called stack, and it's going to take in an int x, which is going to be the item that we want to insert at the bottom of the stack. So this is obviously going to be recursive because there's no other real way to do it. So, and that's how we discussed we're going to do it. So we want to start with our base case. In this case, our base case is going to be when the stack is empty. And when the stack is empty, we want to push x onto the stack and then return so that we can push all the other elements back onto the stack and rebuild the stack, basically. So we can say if stack.isEmpty, then all we have to do is stack.pushX and return. And this way, as long as we are popping an element every turn, we know that we're going to eventually reach our base case because we're eventually going to consume all the elements in the stack. And then otherwise, we want to save our current item. We want to pop an item from the stack, save that into some temporary variable, and then call this recursively, because we're going to do that, and then on each recursive call, we're going to save off the top element of the stack so that we can then push it on when we return from our recursive call. So we're going to say int temp equals stack.pop, and now we're going to do our recursive call. So insert at bottom, and we're going to put stack and x again. And in this case, stack is now 1 shorter than it was before, right? Because we've popped off an element. And finally, we're just going to push temp back onto the stack. So stack.push temp, like this. And as you can see, this is going to recurse through, and we're going to pop off the elements. We're going to go all the way until our stack is empty and push on X, and then we're going to push all of the values that we popped off back onto the stack in the same order that we popped them off. And we now need to use this to actually reverse the stack. And as we talked about, what we want to do is we're going to go through the stack in reverse order, and then we are going to call this to add each element back into the stack. So we're going to call this, I'm going to make this public because this is going to be the method that you're actually going to call to reverse the stack, and this method is just a helper method that's being called by our reverse method. But that's going to return a stack, and I'm just going to call it reverse, and it's going to take in stack like this. So what do we need to do? The first thing we need to do is, obviously, we need a base case, and if the base case again is going to be if the stack is empty, and if the stack is empty, then we don't actually need to do anything at all. We can just return our existing stack, which is going to be an empty stack. And we don't want to. You could also say like, oh, just like return a new stack, but again, the way that we're supposed to be doing this problem is we don't want to create any additional data structures. So we're just going to say if stack.isEmpty, then return stack. And this is where we're going to add back our elements that we've popped off. And then the next thing we need to do is we're going to save off the value. We're going to pop off a value and then do the recursive call. So we're basically doing the same thing again, as we were doing in the other, in our helper method. We're going to do temp equals stack.pop. But in this case, we're going to call our recursive method again, right? We're going to do reverse stack, and then we're going to do insert at bottom. So at bottom, stack, and temp. And so let's look at what we're doing here, right? We're going to recurse all the way to the bottom of the stack first. And then we're going to return back up. So we're starting at the bottom of the stack, and we're going to call insert bottom first on the last element in the stack. And then each time we return from this reverse stack, we're going to return up one element in the stack, and we're going to call insert at bottom. And then our temp is obviously the variable that we popped off, or the value that we popped off the stack. So we want to return that to the stack at the bottom, which is again what we discussed. And then finally, all we need to do is return stack. And that's actually all there is to this problem. So even though it's I think conceptually it's a very tricky problem. You're sort of doing this like double recursion because you're doing recursion within recursion. But the code itself is not very complicated, which goes to show that most of these problems that you're going to do for a coding interview, you're not going to write a ton of code. And the reason for that, obviously, is that you don't have time to write a ton of code. Like I just did this in 15 minutes, and that's sort of, and I obviously thought about this problem a little bit before recording this video, but the idea is that it shouldn't take you more than half an hour or an hour to do whatever the problem is for your interview. So if you find yourself spending a lot of time and not making any progress, or you feel like you're going down the wrong route, or maybe things just like, it seems like it's getting really complicated, it's good to like take a step back and just think about, am I approaching this the right way, or is there an alternate approach that I could take? So let's go ahead and actually go through an example and just test our code to make sure that it works the way we expect. I'm just going to do this short stack because I don't want it, otherwise it could take a very long time. So this is going to be our stack, and we're going to call reverse stack. So I'm actually going to say that stack equals 1, 2, 3 like this, because it's going to be slightly easier to represent. And so we're going to say if stack is empty, which it's not. So temp equals stack.pop. So now temp equals 1 and stack equals 2, 3. So we're going to call reverse stack. So stack equals 2, 3. the stack is not empty, temp equals 2. And then we're going to, again, call reverse stack, which now is stack equals 3. So we're going, and then it's not empty again. And we're going to pop that. So temp equals 3. And now stack is empty. So we're going to say stack is empty, and we're going to return stack. So we return the empty stack, and then we come down to here, and we say insert at bottom of the empty stack. So stack, we're now here, stack is the empty stack, and we're going to insert at bottom temp, which is 3. So to insert at bottom, we say if stack is empty, which it is in this case, stack.push x. So now stack equals 3, like this here, and we return back to here, and we return our stack, which is 3. And now we are in this call we just returned from reverse stack, and stack equals 3. So we call insert at bottom, stack is 3 and temp is 2. And now stack is not empty, so we say that temp equals stack.pop, so temp equals 3. And now insert at bottom stack, which is now empty, and x. So and in this case, x is 2. So we're going to say stack is empty now, so stack.push 2. So stack equals 2, and now we return, and we come back to here where temp equals 3 and stack.push temp. So our stack is now equal to 3, 2, like this. And then we're going to return back another level to the top level, and we're going to, so now we returned back from reverse here. And obviously this gets a little complicated, so drawing it out on the board is really helpful, and I'm just going through it pretty quickly, but it would be good to go through it on your own time and make sure that this all really makes sense. But finally, we are here, and we're going to call insert at bottom stack, which is this, and temp, which is 1. So we come down here, stack is not empty, temp equals 3, stack equals 2, temp, we're going to do the same thing again, so temp equals 2, stack is empty now, so we push on the 1. So stack equals 1, and then now we come back to, we pop up one level and we push temp, so we get this. And now we come up one level again and we push temp again, so stack is now equal to this. And then we return stack, or we actually don't return, sorry. We are modifying the stack in place, but in Java we have a pointer to the stack. So it's going to get modified in place here, and then we break out of insert at bottom, and our stack is now equal to this. And so we're going to return stack, and we reversed it the way that we expect to. So that's basically it. The last thing we should do is look at the time complexity and space complexity of this problem. And this is a little tricky because there are these two parts, but the best way I think to do it is to break it down into the two parts. So I'm going to look at the space and time complexity for insert at bottom first, and then we can see the space and time complexity for this. For reverse is going to be whatever it is times the space or time complexity of, or sorry, times the time complexity plus the space complexity of insert at bottom. So let's look at time complexity first. For insert at bottom, we see that we are going through all of the nodes one time, right? Because we're recursing down, we're hitting each node, and then we're returning back up. So we basically do a push and a pop for each node in the stack. So the runtime of this is just n, right? So insert at bottom is just O of n, because we're going to go through all the elements in the stack once. And then the runtime for this is also, in this case, we're going to go through all the nodes once, right? Because we're going to traverse the entire stack, but then we're going to say for each node, we call insert at bottom, right? We're going to go through all the nodes and call a function that takes O of n time. And that means that we're going to if you just considered that, if you ignored the insert at bottom, then this would take big O of n time. But we're going to do insert at bottom big O of n times, right? So we end up with reverse is going to be O of n times O of n, or it's going to be O of n squared. So we have a quadratic time algorithm here, which is not good per se, but in this case, it's going to be the best we're going to do because of our constraints on what we can actually do, right? Because we talked about how if we could use another stack, then this would take linear time. And now let's look at time. So this is time. And now let's look at space complexity. So I'll do the same thing again. We're going to say insert at bottom. And again, so we're going to recurse down through our stack. And so let's say that we are at this point where the stack is empty. That means that every item in the stack has had to be stored in the, every item in the stack has had to be stored in the call stack, right? So every item has had to be stored in memory, even though we don't have like a data structure for it, or it's not in a data structure. So that is, again, there are n elements, so that's going to take big O of n space to actually store that. And that means that this is going to be big O of n in terms of space complexity. And then again, we'll do reverse. So this is going to be slightly different than before because we're going to call reverse, and as we discussed a moment ago, it's also going to go through all n, and it's going to have to store all n items in the call stack. But unlike with the time complexity, we're not actually going to have to multiply that by the insert at bottom, because insert at bottom is not getting called multiple times at once. It's only getting called, or multiple times from here. It's only getting called once from here, and that means that we're not going to have the space from n calls of that at the same time, because we're going to call this once and it's going to take up n space, and then it's going to free that space, and then we're going to call it again and it's going to take up n space, and we're going to free that space. So that's actually just going to be an additional O of n space on top of the O of n that we're using here. So we're actually going to get O of n plus O of n, which is going to be obviously O of 2n or O of n. And hopefully you can see why that works the way that it does, because in this case, unlike with the time complexity, we're reusing the same space over and over again for each call to insert at bottom. So hopefully that question made sense. It's a little tricky. If you have any questions or comments, I've been getting some good comments recently and I love answering them. So let me know in the comments below on the video or on the blog. Either way is fine, and I'll be sure to get back to you. Or you can tweet me at ByteByByteBlog, and that's also in the YouTube comments below. And I look forward to seeing you guys again soon.